All right, well, welcome back to the next video. I went ahead and posted the next assignment up on Canvas. So if you haven't noticed that, that is up now. You can take a look at it. Essentially, the next assignment is going to cover what we talked about in the last video, as far as looking at influential observations, as well as this video on transforms. And so it'll ask you to do exactly the same thing that we've done together, except with your particular data set and your variables that you have that you've collected data on. So it's just repeating what we have done. So hopefully you take good notes. Of course, feel free to look back at the videos and and see what you need to do so that you can do a good job with that assignment. And of course, let me know if you have any questions as well. All right, so I'm going to scroll down here. So you'll see that video posted that finished up what we did on Wednesday. Let's go ahead and go into transforms for today. Now we've talked about transforms a little bit, so I don't think this is going to be an incredibly long video, probably about an hour or so, but we'll go through an example as well. We're going to approach it from a model perspective, right? So looking at our assumptions from the model level rather than the individual variable level. But you'll notice that the same type of transforms, whether it's power greater than 1 or power greater than less than 1, right? Exponent greater than 1 or exponent less than 1. It's the same as we talked about in 7050. And we're going to add logs and inverses in here as well, because sometimes those can be helpful as transforms. But for the most part, what we talk about isn't going to be too mind-blowing. I think we're really going to get into how to do it with multiple predictive variables. That'll be a little bit different, and then we're going to add also to our model comparison table. So we'll look at the same variables that we've been using in that last video, and we're going to add another model here, maybe a couple more models here when we have some transforms. And so again, it's hard to know exactly how it's going to turn out because you selected what our predictors are, what our outcome is, but we're going to see if we can get a good comparison across multiple models, which is really where we want to go with this course and into your next courses, whether it's 8050 or 8060 or another course like SEM or whatever it may be, because we should be looking at multiple models, not just one model, and doing only one analysis, right? And so we're trying to move in that particular direction here. And so this will be a good example of that once we get multiple models to take a look at. All right, so I'm going to start with the PowerPoint. So you can open up that PowerPoint there. You already have the diagnostic table, right? That's the one that we've been working on. But let's just talk a little bit, go through these slides, talk a little bit about transforms, and then we'll get into an example. So we're still talking about model violations and essentially how to correct for them at this point, detect them and then correct for them. And so there's a couple concepts that we've learned when it comes to our assumptions of linearity as well as normality that we can kind of tie together. And so one of those concepts is called the rule of the bulge. And so you notice here it kind of looks like a circle or maybe even like a crosshairs from a scope or something like that. But if you're looking at this particular scatter plot in these four quadrants here, you'll notice that if you look at any one quadrant by itself, so this quadrant here at the top right, could be seen as its own XY axis between a predictor and an outcome. So again, predictor on the x-axis, outcome on the y-axis. And you can see in this particular case that this would not represent a linear relationship. This would represent a curvilinear relationship or a nonlinear relationship. It's the same thing if you go down to the bottom right-hand quadrant. If you're just to pull that section out, that curve out, and put it on its own XY axis, you'll see that it also is nonlinear. And so the rule of the bulge is looking at linearity, right? And so what happens, or what do you do, or what are the transforms if you are violating the assumption of linearity? All right, and then we've already talked about transforms already when it comes to normality, right? So we've talked about before that if you have a positively skewed distribution, then what you want to do is you want to take or use a transform to an exponent or power less than 1. If you have a negatively skewed distribution, then you want to take your transform to a power greater than 1. And again, the reason for that is if we're looking at our skewed distributions, right, if I have a positive skew, I want to bring that tail in. And so if I'm taking it to, let's say, all my original values to the square root of x, which is just a power of a half, right? turn that into decimal, it's a power of 0.5, or take it to an exponent of 0.5, that's going to bring that tail in, because that square root, all those high values are not going to get smaller, right? And those lower values aren't going to change as much, even though you take the square root of them. And so that brings that tail in. And the same thing, like if we have a negative skew, so again, the tail is in the negative direction over here on the negative side. In this particular case, we want to stretch out the distribution. And if we stretch out the distribution, then it'll help normalize it. Now, of course, it's going to be a little bit more platykurtic, but that's okay because we're not so much worried about kurtosis. We're more worried about the skew. Kurtosis, the percentages under that distribution are going to be relatively the same. It's only when we have a skew data or non-normal data that those percentages are vastly different. So in this case, right, so we're maybe taking to a power greater than 1, so maybe we're squaring it. Maybe we're taking it to the 10th power or something like that, right? And that stretches out the distribution. So this isn't new, right? We talked about this in 7050, right? And how can we adjust our distributions to make them at least mathematically more normal and maybe appear a little bit more normal. Or we're never ever going to like get a perfectly normal distribution, but something that's within the realm of chance when it comes to normality. And that's all we're really talking about with Tukey's ladder transformations. So this, if we have y, if this is our outcome variable, right? You see it looks like a ladder. We have what's called up the ladder, down the ladder, no transform. If we're going up the ladder, we're increasing variability. So remember, like a negatively skewed distribution. If we go up the ladder, it's a power greater than 1. So we are increasing the variability, stretching out that distribution. And then if we have a positively skewed distribution, we wanted to decrease the variability. We want to bring that tail in, right? Reduce that tail. So we're going to take it to a power less than 1, such as like a square root. So you're like a square root of y here. And just like we're going up the ladder, we are increasing variability. So maybe we take it to the 2nd power or the 3rd power, or take the e to the outcome power. All right, so there's all different types of transforms. And the other direction for is decreasing variability. If we have a positive skew distribution, we can take a log, or we can take an inverse, right? 1 over the outcome variable, 1 over y. And each one of these rungs in Tukey's ladder transformations is represented by a particular power. And so as we go up, we get a power greater than 1. When y equals y, which is equaling itself, so when the outcome equals itself, there's no transform. The power is 1, right? The exponent is 1. Right, and then we have powers that are less than 1, between 0 and -1, which would be like the log as well as the square root. And then we even have some powers that are less than 0, in this case negative values, like this -1 over y. And again, where you go up and down this ladder depends on the severity of the skew that you have. Generally, if you have a positive skew, a log works really, really well. Sometimes a square root will work well also. And so those are probably the most common is the square root and the log. When we go to a power greater than 1, then taking a square in the values, or taking it to the 3rd power or the 5th power, right, will help you out as well. So anyways, that's Tukey's ladder of transformations. If we were to put that on the x-axis, so if we put on its side, so for our predictor, it would look exactly the same, just tilt your head sideways. But if it's on the x-axis and we're looking at it horizontally, but it's the same idea. So up the ladder, we're increasing variability. Down the ladder, we're decreasing it. And the only thing we've really changed here is putting it on its side and replacing y with x, right? And now we're talking about the predictor variable. So you're probably wondering, like, why would we do this? Why did we just turn it on its side? What benefit is that? There actually is a benefit to it, because now if we take this and we apply it to the rule of the bulge, then we can actually combine the rule of the bulge with Tukey's ladder to come up with transforms that not only address normality, but also address linearity at the same time. And so notice what we did here is that if you're looking at the outcome, right, our vertical axes here, we're saying up the ladder on y, down the ladder on y. Again, up the ladder is increasing variation. So if we have like a negative skew, or if we have a nonlinear relationship that looks like one of these 2 top quadrants. Same thing with the bottom 2 quadrants. If we have a nonlinear relationship that looks like one of these 2 bottom quadrants, and we go down the ladder on y, we can also address a positive skew. And so what we're really trying to say here is that when we talk about linearity, when we talk about normality, on the multidimensional space here with multiple predictors, what we're saying is that they're related to each other, right? That you can't really separate the two. That if you do a transform for normality, you are addressing linearity. If you do a transform for linearity, you're impacting the normality of your model. They're tied together. And so if we take these two separate concepts, rule of the bulge, Tukey's ladder, put them together, this is what we get for as a guide to transforms. And so let me see if I can maybe explain how this works visually. So I'm going to focus on the bottom left-hand quadrant, right? So right here, and let's just look at that and see if it makes any particular sense in a particular drawing. So let me switch screens over to Paint. So I'm just going to go ahead and just replicate that quadrant. So again, here's my X, Y axis. We have our regression line between our Y variable and our X variable. Now that line obviously is being fit to observations, so I'll put some dots in here for observations. You can't really see that, but try to make them a little bit bigger. All right, and we'll just say that this line of best fit is meeting these points on our XY scatter plot. All right, and we see that it is a nonlinear curvilinear relationship. But when we look at this, right, I'll use a different color here, but when we actually look at this, because again, you know, if we're looking at a normality for just X or normality for just Y, we're looking at how many observations are in any particular place. And so if I'm looking at the predictor on this x-axis, we're going to see that we're going to encompass more values to the left than we do to the right. It actually becomes less frequent. So essentially, that is a positively skewed distribution, right? And if I'm looking at it from the y-axis, the same thing, right? I'm going to get more, I'll use a different color. I'm going to get a higher frequency of values here than I do at this end. There's going to be more observations here towards the bottom than it is towards the top, which is giving us, in this particular case, a positive skew as well. And so if we're looking at this, then we can say, oh, okay, so then when I address this normality issue, if I, on this x-axis, take, let's say, a log, I'm going to bring the tail in this way. If I'm doing the same thing on y, and I'm doing a log of y, I'm going to bring the tail in this way as well. And so I address the normality issue with my log transforms on x and y, but at the same time, I end up straightening out the distribution so that it's no longer nonlinear, but now is a linear relationship between the two. So I know that looks like just a jumbled mess of lines, but just realize that when we put a nonlinear line, right, it's representing some level of distribution, in this case a skewed distribution, that when we address one, we address the other. And that's really what our rule of the bulge and Tukey's ladder combined together is addressing. So address one, I address the other because they're tied together. Okay, so now going back to our slide here, so again, if we're focused on this bottom left-hand quadrant, down here, what we just looked at, notice that that's down the ladder on y, and it's also down the ladder on x. So if I'm looking at just the x-axis, I'm in the negative direction. It's down the ladder on x. I'm looking at the y-axis, it's down the ladder on y. So if I'm down the ladder, again, on x, I'm using a transform of a power less than 1. Right? Maybe it's a square root, maybe it's a log, but I'm down on y. So look at this as on x. So here's the x-axis, right? We're at less than 0, we're in the negative direction, we're down the ladder, we're decreasing variation, so we're taking like a log. Same thing with y, right? So again, we're in that bottom quadrant, which is down here if we're looking at this as a vertical axis. And we're going to notice that, okay, my transform that I should be doing is a power less than 1. Right? And so in this case, a log for both x and y would probably be best, and not only addressing our linearity, right, a violation, so making this nonlinear to a linear relationship, but also addressing the normality issue as well. So just remember between these two that they're related. Linearity and normality is related. You address one, you address the other. So if you're looking at your residual scatter plot, and you notice that it's a nonlinear relationship, and you make an adjustment for it, it's also going to impact the normality of your model as well. So they're tied together. Dress one, you dress the other. And hopefully we'll be able to demonstrate that today, depending on how our variables turn out. Okay, so in regression, right, basically it's association between two variables in simple linear regression, right, predictor and an outcome. And so we can choose which variable to transform. Now in simple linear regression, transforming X or Y really doesn't matter when it comes to our interpretation. Not really a big deal. But once you get into multiple regression with several predictors, it does become a little bit more complicated. And so typically, if we have to choose whether we're going to transform the predictor or the outcome, we would typically prefer the predictors over the outcome. And so transforms on the outcome of the Y variable tend to be a little bit more difficult to interpret. And I'm not sure necessarily it's more difficult to interpret. I don't really think it's more difficult to interpret, but it requires another level of analysis. And I think that's what everyone's really concerned about, that I have to do additional calculations in order to interpret it. And so, and we all don't like to do additional calculations if we can help it. So just generally, again, when it comes to interpretation, we tend to prefer to do our transforms on the predictors rather than the outcomes. But like I said, I mean, if you don't mind a little extra math, transforms on the outcome is just fine. Okay, some things to remember when you are transforming. So some values cannot be transformed. So example, a log of 0 is a non-existent value. So if you take a log of your variable and it has a 0 in it, then when you transfer it over, that 0 is going to become a missing value. And so you don't want to do that because that's going to make you lose observations, lose statistical power, and lose data. So not ideal. So if that does happen, right? So if you do have zeros in your data set and you want to do a log, that's fine. Just add a constant, right? Just make it non-zero. So if you have like a -3, we'll add 4, right? And then that's going to turn all your values to be positive values greater than 0. If you have a 0 in your data set and you want to do a log, make sure you add at least 1, right? If you add 1, then now your values aren't going to have any zeros. It'll start at 1 instead of 0. And so as long as you're doing whatever math that you do to your observations, as long as you do it to all of them, you're going to be just fine. It's like when you do a transform, if you take the square root of all your observations, then you're going to be just fine. If you add a value to all of your observations, then it's going to be fine. You just have to be consistent that you do any type of adjustment, that you do it to all the observations, not just some of them. If after a transform doesn't quite fit, then you can always try to do like an under transform, right? You know, under transform you can add a constant, over transform you can subtract. I haven't had a lot of success for this because it really depends on the values that you have and it's relative to those values. And so it's just easier for me just to do either a little bit stronger or a little bit weaker transform as opposed to doing adding and subtracting. But you know, you can make small adjustments if you add and subtract constants. Something to remember, so not only does the log of 0 does not exist, but an inverse of 0 does not exist as well. So you got to make sure you add a constant if you're doing any type of inversing. And then also for a transform, and then also square roots, negative numbers do not exist. So you got to add a constant as well. Square root of 0 is fine. Square root of -1 is not going to work. So you got to make sure you have at least 0 and above in your data. And again, you can just add constants to meet those requirements. Let's talk about logs just a little bit, just so you have an idea how the math works. I'm not sure if I want to go through every single one of this. I think the explanation here is probably more complicated than what's really going on. So I'll try to simplify this a little bit. So if I'm doing a log base 10, right, and that's what this very first set of examples are. So my original data, I have an observation that gives me a value of 10. So someone says 10 on whatever count it is or whatever it is that we're measuring. If I take the log of 10, I'm going to get 1. So notice what it ends up equaling is the exponent. The log of 100 is 2. In other words, 10 times 10, 10 to the second power. Right, and then 10 times 10 is 100, right? So that makes sense. 1,000 is 10 to the third power. So someone who says 1,000 in their response, right, is going to change that observation value from 1,000 to 3. So it's changing it to the exponent of the base, right? In this case, a log base 10. Same thing if you have a log base 2, right? You can do any base, so it doesn't have to be 10 or 2, it could be 5, whatever. But it's always going to change it to the exponent. So again, if someone gives it 2, then that's going to change it to a value of 1. A value of 4 is going to change it to a value of 2, which is the exponent. A value of 8 is going to change it to a value of 3. Again, the exponent. 2 times 2 is 4 times 2 is 8, right? But it just changes it from the value that is originally in the data set to the exponent at the base value that you specify, whether it's base 2 or base 10. Right, and you see that here again with the last set. I think this next one is a little bit more visual. Right, so again, if you're thinking about a positive skew, you have outliers out here, really large values. Income is a really good example of this. Right, income is not a normally distributed variable, very much a positive skew. And so you have these really extreme large numbers of people who are in the, the upper class, right, and make it difficult to do analyses with. And so if we do a log of it, then we can make it a little bit easier for us to work with and help normalize that distribution. So a log of 1 would give us 0. This again, base 10. A log of 10 would give us 1. Remember the exponent, right? 10 to the 1 is 10. 10 to the 2 is 100. So a value of 100 becomes 2. Value of 1,000 becomes 3. Value of 10,000 becomes 4. Value of 100,000 becomes 5. And just notice how we just compress that distribution. We've taken that skew and we just really squeezed it down. So this works really well with income because income uses very large numbers, and we reduce something like 100,000 down to 5, right? 1,000,000 down to 6, right? And that really is going to squeeze that tail down and help normalize the distribution. And so again, original values at the top, the log values at the bottom. And so we end up doing our analysis on the log values, which gets rid of that long extended tail due to outliers. So the transforms, if we're doing a log or even a square or even a square root, whatever it may be, it still preserves the ranks, and this is why it works. We apply the transform to all observations, so it's equally applied, right? And it maintains the ranks. That the largest values remain the largest values, the smallest values stay the smallest values. The only thing that's changing is the relative distance between the points. As long as that relative difference change is consistent, such as a log or a root or a square, right? As long as it's the same, then it's going to work well. It's going to reduce that skew and still maintain the ranks and make us be able to work with it and help normalize that distribution. Let's see some common log bases: log 10, log 2, log to the those are all common bases. E, I think if I remember correctly, is like 2.71 or 2.72. Repeated. I'm not repeated, but continual decimals. It doesn't end. But someplace around there. It's something that occurs naturally in our environment, and so that's why it's a popular one. All right, so original values must be greater than 0 for all those log bases. We talked about that already. Just remember that. All right, so what about interpretation? So if you do a log on one of your variables or both your variables, whether it's predictor or outcome, how does that change your interpretations? Changes it a little bit. Just remember, again, when we say B here, B is the regression coefficient. So if we log both X and Y, right? So if we log the predictor and the outcome variable, when we talk about that interpretation of that B coefficient, of that unstandardized coefficient from the regression equation, we're going to say the coefficient percent change in the outcome for every 1% change in the predictor. Remember before it was like 1 unit change in X, right? The B value change in Y, the B value change in the outcome for every 1 unit change in X. It's still the same idea, except now we talk about it in terms of percents. So it's the coefficient percent, take the coefficient from your regression output, give it the percent, it's going to tell us the change in the outcome for every 1% change in X. Right, so if our coefficient, our slope was 0.23, then we would say 0.23% change in the outcome for every 1% change in X. All right, so let's say our predictor is logged, but our outcome is logged, but not the predictor. So I mentioned before, it becomes a problem, it's a little bit harder to interpret. It's not so much harder to interpret, it's that you have to do a little extra math. So what you have to do is you have to convert the slope coefficient, the B value, to a percentage in order for it to make sense. And so in this case, what we do is we take the base 10, We take it to the coefficient in our output, so that slope, right? 10 to the slope, and then we subtract 1. And once we do that, we then multiply it by 100 to get the percent. So that's going to tell us the percent change. And notice that we're going to say here for every 1 unit change in the predictor. Right, I'm going to say 1 unit change in the predictor because it wasn't transformed, right? Just the outcome was transformed. So the wording change is in the outcome, but not the predictor, right? But we have to do that conversion to a percentage, right? And that's where the part it says is more difficult to interpret. It's not so much as more difficult to interpret, is that it requires extra work, right? It requires an extra calculation. Okay, and the last one is, well, what if your predictor is logged, but your outcome is not logged? Well, in that case, notice here we don't talk about percents when it comes to the outcome, to the y value. We're just going to say this, the regression coefficient b value change in the outcome for a 10-fold change in x, and that's if your base was 10. If it was 2, we would say for a 2-fold change in x, right? And so again, exponentially, right? A fold is essentially is taking it to a power. So a 2-fold is taking your value and squaring it, right? A 3-fold would be squaring it and then squaring it again, right? And so that's what I mean by a fold. And so note again, when we do log transforms, it does impact how we interpret that coefficient, the slope coefficient that comes out in our output. So just be aware of that wording if you use a log transform. Okay, so we talked about looking at different models, measuring and fitting different models, and then comparing them to each other. And so these are the types of questions you want to ask when you're comparing models. We call this a sensitivity analysis, right? Like does the adjustment we make, whether it's removing an observation, whether it's doing a transform, whatever it is, does that make a difference? Is it sensitive? Like is the result sensitive to the change that we make? And so if we're comparing our models, three things we want to be looking at. The first is that are the hypothesis test conclusions different? Right, we're talking about significance there, right? So maybe with the untransformed, we're failing to reject the null, but with the transformed version, we're rejecting the null. So in other words, we don't find a difference, but we do our transform, and now we do find a difference. That's a different test conclusion when it comes to significance. The other one is the effect size calculations different? So remember, the effect size is at the individual observation level, individual person level. Is it different in how we make our conclusion? Did we go from a moderate effect to a large effect, or maybe went from a moderate effect to a small effect, right? If our conclusions are different when it comes to our effect size, right, then that may matter in how we compare our models to each other. And then finally, is the difference in the effect size statistically significant? And so effect size can also be used as a hypothesis test if you compare it to chance. And so what we're really saying here is there a difference in the effect size? And we can test this statistically as long as we turn that change in the effect size, the change in the R-squared value, to an f-test. All right, and that's what this next slide is about. So if all things are equal, we can look at our models, conduct an f-test on the change in R-squared, or the difference in the effect size, right, and see if that difference is significant. So here's a formula. We need to get an f statistic, and this is the formula that we would use. Right, there are some calculators available, but this is not a hard calculation. So we'll use both a website, but also do a little bit of hand calculating as well. But we'll just take that change in R-squared, or the difference in the R-squared values between two models. We'll multiply it by the degrees of freedom from the model that has the most parameters, or the most degrees of freedom, just depending on what we're comparing. So basically the larger model. And then we're going to divide by 1 minus the R-squared value from the R-squared value that's largest of the two. And so we'll go through an example of this when we go look at some data here in a little bit. All right, and then once we get that F statistic, when we calculate it, we then look online at the calculator to see what the p-value is, to see if that change is significant or not. Again, if it's not significant, then our models are determined to be equivalent, right? And so if they're equivalent, it doesn't really matter which model we use, and so usually we want the one that's most efficient, right? The one that is more concise. Which brings us to this last slide here before we get into an example. So if we're comparing our models together, all things are equal. If all things are equal, then we're going to report the model with the easiest interpretation that retains the most data. So this is usually going to be the untransformed model with no data removed. So if all things are being equal, right, the statistical conclusions are the same, the effect size conclusions are the same. We calculate an F statistic between the two models. We find that there's no difference. If all things are equal, then we are going to report the untransformed with no data removed. We retain every observation, we retain our statistical power, right? And we use the model that we can interpret without talking about percents or doing conversions or anything like that. So again, all things equal, Occam razor, right? The simplest explanation is best, so go with the easiest or simplest model. If our models differ by statistical decisions or the effect size, then we got to weigh the evidence of the assumption violations and the data loss, right? And so just because we find two significant predictors with one model and only one with the other, doesn't mean that the two predictor model is best. We have to look at the assumption violations. That should be determining whether or not we accept a model, not the outcome. And I see this all the time, especially when you get into upper level classes or in your labs, where you're comparing multiple models to each other. Maybe you're doing SEM or something like that, and you choose the one with the highest R-squared value. That should not be how you choose your models, right? You choose your models based on the assumptions, based on how confident you are you're meeting those assumptions, right? You're gonna have more confidence in a model that meets the assumptions than one that doesn't meet the assumptions. And so that's what we should be doing to make our decisions, not the one that has the highest R-squared or gives us the most significant predictors, because it could be completely erroneous, right? Because those R-squared values and those significant predictors may not hold if we meet the assumptions of the test, right? And so assumption violations and data loss should be determining or driving our decision on which model is best, not R-squared values. Okay, so if we have models that meet the assumptions with no data loss, then that is preferred over models that meet the assumptions with data loss, right? So we give preference to no data loss over data loss. We also give preference over more assumptions that are met. I think that goes without saying. Any models that are chosen with data loss, we need to justify or explain why we're removing data. Why are we saying that this data is not important or that it's an error, right? So we need to justify any data removal that we have. We want to retain as much data as possible. And of course, we can always report both models, right? We can say in our write-up, this is the one that I feel is the best given these evidences, but then report both models in a table in the appendix. That allows the reader to make their own decisions to either agree with you or disagree with you, right? And be able to take their own conclusions from your work, which is really what we want. We want our readers, our audience, to be thinkers, right, and not just take what we say at face value, because we think it may not necessarily be best, and it certainly may not be best in their situation that they're trying to apply the research that you did too. Okay, so again, our decisions for model selection should not be made based on statistics. What I mean by that, should not be made based on significance, should not be made off of higher R-squared values, right, or effect size conclusions, but rather on how solid the model is in relation to the assumptions that are being met or not being met. That should be how decisions for models should be. Unfortunately, not a practice that is used very often in academia. Again, because we want to be published, and so higher R-squared values, more significant predictors, helps us get into that publishing market, as opposed to talking about assumptions, right? But ultimately, assumptions should be how we're, the model fit, and then the assumptions that it has should be the most important aspect, not so much the statistical conclusions. Okay, so I've talked enough here. Let's go ahead and get into an example. So we're just going to continue from what we did in that last video. So we're going to add a third model here. This model is going to be model number 3. And again, I highly recommend that you follow along with this as well, so that you know how to do it when it comes time to do your assignment. So model 3 is going to be our transform model. And we're going to do a transform model here because we already know with model number 1 that we violated normality. Right, we can see that. We can also see in our residual plot we're not doing too well. Like symmetry is off, equal variance is off, we're not meeting linearity, we have a positive skew here, we have potentially some influential observations, right? And so before we just go with this model, we should look at a model where we try to correct some of those assumption violations. So that's going to be our model 3, our transform model. So I went ahead and just opened up the same data that we've been working on. I went back to our original data, so you're going to notice here participant number 9 is back in this data set. All right, so we want to do our transformed with the data set with all the observations. So you can just download a fresh SPSS file, and we'll work from there. All right, and so we already know going to this that we already have some assumption violations. We already know that we're going to do transforms. What we don't know is which variables are we going to transform, right? Which ones would be best when it comes to doing a transform? Like which ones are we going to do like a log or a squared value, right? Power greater than 1, whatever it may be. We don't know that yet. So the only way we're going to find that out is if we get our descriptive statistics and we determine things like normality of the individual variables. All right, so we'll go to analyze, go to descriptive statistics, get our frequencies. All right, uncheck this display frequency tables, and let's go ahead and get our variables. So our outcome is sleep, so I'll put that in there. We had credit hours, we had work hours, we had study hours, and we had social media. We're just going to put all 5 of our variables in there, and all we're going to do is get some descriptives, and we're just going to focus on normality here in this particular case. So we'll get our mean, median, we'll get our skewness statistic, get our standard deviation, the minimum value, the maximum value. We don't need the standard error of the estimate here, but just remember if you're looking at residuals, you do want to make sure you check that box. Okay, so that's all we need to hit continue. We do want to get some charts because again, we want to visually inspect as well, not just look at the numbers. Although visual inspection is more subjective, there are times where our numbers tell us it looks like it's normal, and then we look at the graph and we realize, well, that's not normally distributed at all. Okay, then we click OK. All right, and let's take a look at our output. So again, we can look at means and medians. I don't want to spend all that time here. You can look at those on your own time. I'm just going to jump right to the skewness statistic and the standard error of the skewness. We'll go from there and see if we can't make some decisions about normality and try to decide which variables would be best to do a transform on. And so if we're looking at hours of sleep in a typical night, we have a skewness statistic of 0.154. The standard error of the skewness is 0.34. So remember, 2 standard errors away from 0 will give us the range of what we consider to be a normal distribution. So if I double that, so I take 0.34 and double it, I get 0.68. So if my skewness statistic falls between plus and minus 0.68, I'll just say that it is normally distributed. That is the case here. 0.15 does fall between negative and positive 0.68. So it looks like hours of sleep seems to be normally distributed, at least based off the numbers. If we look at credit hours, right? Credit hours, we get 0.33, multiply that by 2, I get 0.66. So plus and minus 0.66 is my range of normality. We get a value of 0.57. It looks like credit hours is normal enough. Right? It's getting close to not being normal, but it's normal enough for us to continue with what we have. Same thing when it comes to hours worked per week. You get 0.33 for the standard error. Go ahead and double that, we get 0.66. In this particular case, it looks like 0.63 does fall within that range, but not by much, right? It's barely within what we consider to be a normal distribution. All right, and then if we're looking at number of study hours in a week, same thing, we get 0.68. 0.53 does fall within our range of normality, so it looks like we're probably okay there as well. And then our last one, which is going to be hours spent on social media in a day, again 0.66, but notice that skewness statistic is 1.96, so it falls outside of our range of normality. So it looks like the variable that we definitely want to consider getting a transform on is probably going to be this hours spent on social media in a day. Okay, so with that being said, let's look at this last variable, hours spent on social media. We're going to focus on this particular variable. It is a predictor variable. So remember we said, if we had to choose between outcome and predictors, which one would we want to transform? Certainly in this case, predictor would be preferred, so we don't have to do any extra calculations and interpretation. Um, but it's the only one that seems to be exceeding our range of normality. Although we could technically make adjustments, slight adjustments to all of them if we wanted to try to get it a little bit closer to a skewness statistic of 0. But within the confines of the model, we're going to start with just this one variable and see how that impacts our findings of this particular research question. Okay, so it looks like a positive skew here. We should probably look at, I'm sorry, we should look at the graphs. I skipped that part. Let's look at our graphs really quick, see if there's anything here that we're particularly concerned about. So if we're looking at hours of sleep, that looks normal enough, right? It's obviously, again, not a perfect normal. There's a little bit of a right-hand skew, but we saw that in the statistic. Same thing here with credit hours. We are beginning to see a tail here, right? And so if we wanted to clean this up a little bit, we could try to do that. I'm going to leave it alone for right now, just given all of our variables, not to make this too complicated. Here, this one is interesting. So if I'm looking at average work hours, you're going to notice that there's a pretty severe skew in the sense that there's a whole lot of students who are not working, right? And so we have this high frequency at 0, and then everything else actually looks like it's it's fairly spread out there. Definitely a little bit of a tail in the positive direction, which we kind of would, I guess, suspect with hours worked per week when it comes to students. So there's definitely a skew here. Given that this is pretty bad, this might be one that we go ahead and do a transform on as well. I'd probably recommend it. Now you're going to find variables sometimes that have this where you have a high frequency at 0, and then you have other counts. So essentially, it becomes 2 research questions here. Really, the research question is what if students are working versus not working, right? So 0 versus any other value of hours worked per week. And then if they are working, how might that impact, say, let's say sleep or something like that? So we end up with 2 research questions here. There are ways to handle these types of data. One is to do separate analyses, where one is looking at work versus not work, and then another analysis is looking at, well, if you work, what impact of hours does that have? We're not going to cover that in this class, but it is definitely an interesting topic to discuss, when you see this in your particular data. But given that this is definitely not normal, not a non-normal distribution, we're going to do a transform on this. It's not going to impact, obviously, we're not going to change our zeros or anything like that, right? But it may impact our other values. So we'll do a transform on that one too. It comes to study hours. Again, not a perfect normal distribution. It is slightly off. We saw that in the skew statistic as well, but for the sake of this example, we won't worry about a transform on this variable. And then obviously hours spent on social media, we had that very large skew in the skewness statistic. We see it here in the graph. There is a tail in that positive direction. It's quite pronounced. So definitely social media should be a variable that we do a transform on. Okay, so overall conclusion in this case, I say let's go ahead and do a transform on work hours, and let's do a transform on social media, and see if we can't improve our model in terms of the assumptions, and see if we can get more confidence in our output and our analysis. Okay, so if we're going to do some transforms here, we need to decide what those transforms are going to be. So we have a positive skew here for work hours. Again, we have a lot of frequency at 0. And so let's just do some log transforms, because I know we've seen some square and square root transforms before. Let's do a log transform here. Again, positive skew means that if we're looking at Tukey's ladder, go back up there really quick. So if I have a positive skew, right? Oops, sorry, we'll go here. So a positive skew on X is going to be a bulk on the left-hand side with a tail in the positive direction. So we're going to be going down the ladder on X. All right. Again, using what we already know with our rules of thumb, that we want to take it to a power less than 1. So we could do like a square root, we can do a log, we can do an inverse. Like I mentioned before, let's do a log here so that we can decrease the variability, bring that tail in. And again, a log because we've seen a square root transform before in 7050. Let's see what it looks like with a log. A log is a more powerful transform as well. Okay, and then we'll do a log also of social media. So let's go to transform. We're going to go to compute variable. So we're going to have our work hours. I'm just going to do WRK, and then I'm going to say, actually, we got to add a constant, right? So we got to do a constant. We're going to add 1. So remember, work hours, we had some zeros. People who are not working cannot take a log of 0. So before we get our log, we do have to do a adjustment. We have to add a constant to it. So make sure you don't forget to do that. Whenever you have zeros in your data set, they have to be positive values, non-zero values if you're going to do a log. Okay, so I'm just going to take my work hours, and quite literally, we're just going to add 1. So I'm going to hit the plus sign on my keyboard, and 1. So variable plus 1 is going to add 1 to every observation. So a value of 1 to every observation in the data set. And I'll click OK. Let's look at our data really quick and see how that adjusted it. So if my work hours was 0 and now became 1, if it was 28 and now became 29, so on and so forth. So now I have no zeros in my work hours variable. Once I do that, then I can go ahead and create my logged value. So this will be work hours log. If I want, I could put like 10 for base 10. That would be fine as well. I'm going to delete my numeric expression here. I'm going to go look for my log transform. You can get that if you scroll through. It's in alphabetical, but sometimes that takes a while. If you remember that it's in arithmetic, then you can click on that subgroup, and you'll see that LG10 is your log base 10. So I'll double click it, and then I'm just going to drag over my new work variable once I've added that constant to it. And now when I get my log, I'm not going to be missing any values because I've added that constant. So I'll click OK. Come back, look at it. Notice my work hours logged. Any value of 1 now became 0, right? Because remember, 0 would become non-existent. So we added that constant. If I had a value of, let's say, 10 in my data set, I'm not sure if I have 10 hours in here. I don't see one. I have 11. That's really close. Then if I had a value of 10, remember, it would become 1. Here's really close to that. It's 1.04 once you do that log transform. So it looks like it worked. It looks like it worked well. Let's get that other variable. Okay, so compute variable, transform compute variable. Now we're going to get our log of social media. I'm just going to change out. So notice I changed the name of the variable. I'm just going to change out the variable here. And so we want social media. So log base 10 of social media. Go ahead and click continue. Right, and then now I have my transformed social media and I have my transformed work hours. Okay, so now we're going to go ahead and fit our model number 3. So we're going to do exactly the same thing as we did before. We'll go analyze. We're going to go regression. We'll go linear. We will put hours sleep in the dependent variable box. We'll go ahead and put in our 4 predictors. We'll put in credit hours. We are going to not put in work hours here, but rather the work hours logged. We're going to put in our study hours. And we're going to put our social media logged into our independent variable box. Go up to your statistics. We'll get our confidence intervals just out of practice. Get our descriptive statistics as well. And then we'll click continue. Under save, we're going to get our studentized residuals. We're just going to check those while we're here because remember they're in our comparison table. And we'll get our distances, Mulholland Novus, Cooks, and leverage. Click continue. And then I think that's it, right? Oh, we need our plots. So don't forget plots. Get our Z predicted value. And then get our studentized residuals. Don't forget your histogram and normal probability plot. Click continue. Okay, we have everything we need. Let's go ahead and click OK. Let's look at some output. So again, we're going to try to fill in this table. So model information, let's see what our predictors are. We know we have 4. Let's see how many of them are significant. We'll report our squared value, and we'll report our degrees of freedom, which we already know is 39 because it's the same model as the first model. We haven't removed anything, just different predictors. So degrees of freedom are going to be the same. And we can find that in the output as well. if you would like. But let's go look, see how we did as far as the overall model information, and then we'll start looking at our assumptions. Okay, so a model summary box, you see our R squared value here. It looks like it's 0.098 or 0.10. So notice that our R squared value reduced from our first model, right, once we did the transform. All right, so we'll see if we do better when it comes to our assumptions, but already we're seeing a decrease in the R squared value. All right, let's take a look at our predictors. So notice here that the overall model is not significant. All right, 0.389, that is not less than 0.05. So it looks like doing this transforms has impacted our overall model. If we look at our coefficients, and look at each of our predictors, note in this case, none of them are significant, right? Which becomes a really good point of why we check our assumptions, because if we were to address those assumptions, there may not be something there that we thought was, or vice versa, there may be something there that we didn't think was there. So in this case, without looking at our assumptions and see if they're any better or anything like that, but just looking at model number 3, we see a difference, right, in our statistical decision. In this particular case, when it comes to our predictors, notice that we don't have any significant predictors now once we corrected for the assumption violation. So that means if we were to go with model number 1, we might be deceiving ourselves in thinking that one of those variables predicted sleep. In reality, it probably doesn't, right? Once we address the model violations, it doesn't look like there's any significant predictors. Okay, but we still have some assumptions to take a look at here, right? So let's start identifying some of those. So if I scroll down, so this is my residual histogram. Notice that there is a bit of a tail here. So may or may not have a skewed distribution. We'll have to check it out. It certainly looks like there might be a bit of a tail, but it may not be at a greater than chance level. We'll have to check it out. PP plot looks pretty good, right? Remember, again, we want it to hug this line. It does kind of deviate just a little bit, but honestly, it's doing a really good job there. So PP plot says it looks like normality is okay. We should probably look at our descriptors for our residuals, which we'll do here in a second. So let me go here. So PP plot looks good. I'm going to put a yes there. Let's look at the residual plot. So it doesn't look too bad because remember before we had questions about linearity, we had questions about equivariance, questions about symmetry. This actually looks pretty good. Obviously there's some unusual observations right here. Notice what it did to that other value that we thought might be unusual. It did bring it in, right? And so if I was to add this to my table, I'd probably say, yeah, there's 2 unusual observations to the right. Is there symmetry? Again, if I'm crossing my eyes, blurring my vision, this almost looks very circular if I'm not counting these 2 unusual observations. So symmetry actually looks pretty good here. If I was to fold this over again because of the uniqueness of the trend that is in the scatter plot, it wouldn't be a perfect symmetry. Obviously, you see that there's some non-overlap over here. Maybe, I mean, over here it looks fine. So it actually looks pretty good. I'll give it a question mark. Those 2 unusual observations are kind of messing things up just a little bit. So I'll give it a question mark. I won't give it a no. It looks pretty good with some deviation, maybe like right up in here. If I was to fold this over, there's some missing stuff. But for the most part, that looks pretty good. Let's see. What about equal variance? Is the spread at any point on X roughly the same? And yeah, again, if I'm not looking at these 2 unusual observations, this almost looks like a square here. Certainly rectangular shape. Doesn't look like it's funneling anywhere. So that actually looks really, really good. I don't know if you'll get anything that looks better than that. So we'll say yes, at least with real data, right? So we'll say yes, that looks good. And then same thing for linearity. Now remember before it's like had this curve to it, and I'm not really seeing that curve here now. Maybe a bit of one right here if you're looking at those unusual observations. But again, if I'm crossing my eyes, blurring my vision, I don't see a nonlinear trend here that's represented by another mathematical function. You know, maybe a slight bend, but for the most part, that actually looks better than our other 2 residual scatter plots. And so that looks pretty good as well. And so already, you know, just addressing that normality issue is addressing some of our other assumption violations. And so this model is looking better. You know, obviously we'll finish it out, but it's looking better already compared to that very first model, which means that we're going to have more confidence in the results of Model 3 than we are going to have in the results of Model 1. I'm going to be more suspicious about this significant predictor in 1 than I will be the lack of significant predictors in model number 3. Okay, so let's look at our descriptives for the residuals. So again, mean should be 0, standard deviation should be around 1. We're going to check it to see if it's normal or not, or normal enough. And then of course we'll look at our influence diagnostics really quick as well. So we'll go to analyze. Let's get our descriptive statistics. I'm going to move these all out for the time being. Let's just put in the residual in here. Everything else should be the same over here in our options, so let's click OK. All right, and let's see what we got here. So mean, is it 0? Yes, it's negative 0.003. Oh, we didn't get our standard errors. Let's go back. We did miss our standard. It's not going to matter here, but let's get our standard errors anyway, just so that we're modeling it. So statistics, don't forget to click that standard error, the mean box, especially when you're looking at residuals. Click continue, click OK. All right, now let's look at it. So again, that standard error, the mean should be between 2 times that standard error, so plus or minus 0.3. Certainly it is, right? And so it looks like we're meeting that assumption. Our standard deviation should be around 1. This is pretty close, right? It is beginning to deviate a little bit more than before, but it is still around 1. It's 1.015 or 1.02. Again, our histogram does give us a little bit of a tail right here. So maybe one value that we're concerned about. Let's look at our skewness statistic. Again, our skewness statistic should fall within 2 times the standard error. So if I'm looking at my standard error, 2 times 0.367 is roughly, right, 0.72. So this is literally like right on the line. It just goes over. It's just barely missing normality. So there is a slight, very slight skew. Again, if we're being very strict here, we say that this is a positively skewed distribution, but this is actually really, really close. We're barely missing it. All right, so if I'm looking at my table, mean equals 0, yes, that looks good. Standard deviation equals 1, yes. Normality, barely, like by the littlest bit, barely missing, right? Looks like maybe a positive skew, but we're barely missing normality. So this is still better than what we had in model number 1, even if there is a little bit of a skew there. All right, so let's check our influence diagnostics here. Let's see if there's any observations that we might be concerned about. Again, in our output, we do have our residuals. So notice there's a 1 underneath it. This is for our first model that we just fit in here. So it's model number 3, but it's the first one that we've done on this data set. So we're going to go ahead and sort that. We're going to look at our most extreme values. We have negative 1.88, and we have this other value of 3.18. So don't forget, we do have an equation for this from our diagnostics PowerPoint. Remember this one right here. When it comes to our studentized residuals, we can plug it into the formula here. Again, I'll spare you the walking through it here, but go ahead and plug through the numbers. I ended up getting, let's see, I think I ended up getting 4.18, which does fall outside of what we consider to be a potential influential observation, and so this is one that is a particular concern to us. So if I compare that value, again, just check, make sure you get the same thing, but if I compare that value of 4.18, look at the critical value in the Stevens article, which should be 3.52, I find that this is a value that is of concern. And so we're going to mark it, let's identify it, and then we're going to mark it in our particular table. So 3.18 gives, that's for participant number 9. So just like before, number 9 seems to be a bit of a concern when it comes to our studentized residuals. If you look at that very next studentized residual, you'll notice that it isn't of concern. And so that's the only value here when it comes to our studentized residuals. We can check our Mahalanobis distance. So we're going to sort it. Again, look at your table in the Stevens article. If you remember, the value of concern is 14 point, I think it was like 95 or something like that, but it was in the 14s. Our highest value here is 10.35. So it doesn't look like there's any observations of concern for Mahalanobis distance. Again, remember Cook's distance is relative, right? So we're looking for large gaps. And so if I'm looking here, I get 0.05, 0.05, 0.06, 0.07, 0.07, 0.08. A bit of a jump here to 0.11. Certainly a jump from there to 0.21, right? And so whether you say participants 48 and 9, or maybe 43, 48 and 9, that is up to interpretation. But just to be conservative, we can say 43, 48, and 9. So again, notice that 9 is showing up just like it was before. So even though our model is looking better, we still have this unusual observation that could be impacting our results. Okay, last one is leverage. So if you remember from the last video, our leverage cutoff was 0.27 or 0.28. When we have all of our data is 0.28, I'm sorry, 0.27, but when we removed an observation, it was 0.28. So let's check out our leverage to see if any values are concerned here. So sort of ascending. Again, our highest value is 0.24. That does not meet 0.27 or 0.28. So it looks like leverage, it looks like it's pretty good. Doesn't look like there's any influential observation, so I'm going to leave that blank. Okay, so here's model number 3, right? We just went through it. I know I went through that a little bit fast, but you can pause the video and double check stuff like that. But just notice here, right, in this particular case, in model number 3 with our transform, we're doing really, really well with our assumptions. We're barely missing with a positive skew. Maybe symmetry slightly off, but it's not terrible, right? Notice that, we're doing better with our influential statistics. Like number 10 just drops off. It's not a concern anymore. But certainly 9 is, right? So 9 is in both places. And so with this particular model, not all things are equal, right? No significant predictors, but it does look like we have an unusual observation that could be influential. So if you're being a good researcher, right, you're not going to stop here. You're going to go to model number 4, which will now be our transformed model without participant 9, right? Without participant 9. And so for this next one, we should remove participant number 9, and then just see how does that compare. Do we get a significant predictor back? Do we not? What's the outcome? But let's remove that one observation. Let's fit it one more time. Obviously, we'll go a little bit quicker now, especially since we know what we're doing. And I'm not going to go ahead and then close out and reopen. You can do that if you like. I'm just going to continue from here. I'm going to remove participant 9. However, if you are working on your own data, I definitely recommend anytime you make an adjustment, remove observations, whatever it is, save it as a new file. So now you have 2 separate files, one with the potential outlier and the one without. And then that way when you compare it, I need to get back to one of those particular data sets, you know which one's which. Okay, so I just went ahead and removed participant number 9. I'm just going to refit everything one more time. I'm going to fly through this again. Right, and so I don't need to change anything here, right? Everything stays the same. The only thing I changed is removing that one observation. So go ahead and click OK. Start looking at my output. We're going to look at our model information first. So overall, our squared value is now 0.15. So it's a little bit higher now that we removed number 9. Notice that overall model is still not significant though. So 0.18 is greater than 0.05. Look at our coefficients. Looks like none of them are technically significant. However, social media log is approaching it, right? And so that's close enough for me to consider that might be something we take a look at. And so if I'm looking at my model comparison table, we still have 4 predictors. Looks like one of them might be a significant predictor. Again, it's close, right? But again, we're assuming, things like normal distributions I could never prove. So we give ourselves a little bit of wiggle room, at least to take a closer look at. We get an R-squared value about 0.15. And it looks like in this case, our degrees of freedom is 38 because we removed that one observation. So we'll just subtract 1. All right, let's look at our PP plot. Let's look at our histogram. Let's look at our residual plot here, see how things are looking. So our histogram for the residuals looks really good. I mean, there is a slight little bend there, but it's hardly that different than a normal distribution. This actually looks really good. We have a stack here, and this is kind of leveled out here rather than stacked, but that's pretty close to symmetry as you're going to get with real data. And so that looks really good. Looking at our PP plot, notice how our observations are hugging that line really, really nicely. So I don't have any concerns about normality there. Let's look at our scatter plot. Notice we got rid of that one unusual observation out here. We still got one here that we may be concerned about, but everything else looks the same, right? So a random spread for the most part, except for this kind of staircase thing that may be indicating a violation of independence, or it could just be an artifact of how we collected data as well. Certainly having a whole bunch of observations of 0 when it comes to work hours isn't going to help what this looks like, because that's going to obviously impact our scatter plot, because it's not a typically continuous normal distribution. But for the most part, right, equal variance, the spread is roughly the same wherever I'm at along the x-axis. Mirror reflection looks really good, so symmetry looks really good. Again, maybe a little bit of a gap up here where we see some below 0 that if we fold it over would kind of show up there as missing, but otherwise that's pretty good, just like it was on the last one. And as far as linearity, I don't see any other mathematical trend that's going to best fit this data other than a straight line. I don't see any obvious curving, and so that looks good as well. Okay, so let's fill in some of this out. PP plot looks great, so we're going to hit yes there. We'll take a look at that in a little bit. Unusual observations, yeah, there's one still. Symmetry looks pretty good. There's a slight deviation where there might be a gap, so I'll just put a question mark, but honestly I'd lean more towards yes there. Equal variance looks good. Linearity looks good. Right, and so if you're looking at our two models from Model 3 to Model 4, they're pretty comparable. All right, let's get a look at our residual descriptives. Again, we'll go to Analyze. Oh, I'm going to point this out really quick. So notice that we did a separate model in the same data set. So you're going to get your residuals, your Mahalanobis, your Cook's distance, your leverage. But notice that's going to be a 2 after it, because this is your second analysis with the same data set. And so we're going to be looking at residuals for 2, Mahalanobis for 2, Cook's for 2, leverage for 2. Just want to point that out just really quick if you see that in your data set. Okay, so we're going to go analyze, go to our descriptive statistics, again, frequencies. I'm going to kick out the studentized residuals for 1. I'm going to put in the studentized residuals for 2. Click OK. Let's take a look at it. Again, it shouldn't be any different than 0, negative 0.0025. It's actually a little bit closer to 0 now that we got rid of that one value. Certainly within plus or minus 0.31. So that looks good. Skewness statistic looks much better at 0.284. So remember last time we barely missed it. It was like just beyond what we considered to be normal. Here it's well within what we consider to be normal. Look at that histogram. Still a little bit of a slight tail in the positive direction. There is that one value, unusual observation, that we could remove just to see if we can't get things to look a little bit better. I'm not going to worry about it here. This is close enough for what we're doing for today. But certainly if we wanted to, we could fit a model number 5 and remove that other observation. Okay, so that looks pretty good. So again, yes, yes, and normality looks good. So this is probably one of our better looking models so far. We can look at our influence diagnostics. I'll save you the time. You know how to do it at this particular point. Sort each of your diagnostics, influence diagnostic variables. So again, studentized residual 2, you can sort. Look at the value that is the highest. It's a 0.270. You can plug that in, make sure it falls within the critical value. It's about 3.52. In this case, it does, right? I'll spare you the calculations here. You can double check it on your own. But nothing for the studentized residuals seems to be a concern. Same thing for Mahalanobis. If I sort it, highest value is 10.33. Remember that cutoff was like 14.92 or something like that. And so that's well within that cutoff. So nothing of concern with Mahalanobis. Cook's distance, remember, we're looking for gaps. Now with Cook's distance, right, usually if we're being conservative, we're always going to find something. But let's see what we got here. All right, so we get 0.7, 0.9, 0.10, 0.10, 0.11, 0.11. Then we've got a big jump right here. And so that's observation number 48. So possibly a concern. Again, but only if we see that value pop up someplace else. All right, then let's sort that last one for leverage. Again, looking at that highest value. If you remember from our previous video, that cutoff was going to be 0.279 or 0.28. This does not exceed it. So this last value here, this value participant number 4, looks like it's within what we consider to be occurring by chance. And so we're not going to put anything there for that test statistic either. Okay, so that looks pretty good, right? So remove that one observation. We're meeting all of our assumptions. Potentially, we have a significant predictor here. Again, we're going to do one more model just to verify if that is something of interest or not. But as we look at this, this model number 4, is the one that we're going to have the most confidence in because it's meeting most of those assumptions. Okay, but we're not done yet, because if you remember, we have 4 predictors, and there's only one predictor that appears to be significant. That means the other 3 non-significant predictors are eating up important variation in our outcome. And it by itself could be masking a stronger relationship or other relationships, or it could be, because of it, we're seeing a relationship that may not actually be significant when it's all by itself. But just remember that non-significant predictors essentially are going to correlate with our outcome by chance and by chance alone. And that sucks up important variation, right? That makes us less confident in the model. So we should do a model number 5 here. This is not something I'll ask you to do on the assignment. I'm only going to ask you to do 3 models on the assignment. So the untransformed, 1 with a removed observation, 1 with a transformed variable, and that's it. And then you can just pick from those 3. But if we were to really get into it and be a good researcher, we would do another model here where we're only going to enter in 1 predictor. And that predictor we're going to enter in is the one that we think is significant. So we're going to bounce out, we're going to remove all of those predictors that are not significant, right? Because they could be impacting this one predictor, right? In a positive or in a negative way, right? That may make it more likely to reject a null or more likely to fail to reject a null. But we're not going to know until we remove it. So, so we'll do that here in model number 5. So model number 5, we're going to say just are logged social media, right? All right, and we'll test it out and just see how it looks. Again, just getting rid of all of the other predictors that are not really predicting anything, right, and are just there. So I'm going to go to analyze. We'll do one more regression, linear. I'm going to kick out all of the predictors that are not our social media logged, because again, that can be impacting our coefficient. We talked about this before. Even with our predictors, there is always some chance correlation, right? And that chance correlation can make our coefficients unstable. So we're going to kick those out. I think everything is good here. Let's click OK. Notice again that because now we fit another model, we're going to have more influential statistics, but now there's going to be a 3 afterwards because this is our 3rd analysis. But just note every time you do analysis, you're going to get a new set of influential statistics in your variable view, in your data view. Sorry, in your data view. All right, so let's see. Let's take a look at our output here. We'll go quickly. Overall, our R-squared value drops to 0.04. Our degrees of freedom in this case are still 38 because we don't have number 9 in there. Let's see. Let's look at our predictor. So social media logged is not significant, right? So what we saw as potentially possibly being significant, remember it missed it. It was like a 0.064 or something like that. It missed it, not by much, but that could mainly be due to the fact that our other predictors were sharing variability and making our coefficient unstable, increasing that standard error just a little bit. So it doesn't look like social media is actually predictive. So we're going to say 0 there. All right. Okay, and then let's just check, make sure our other stuff is looking good when it comes to our diagnostics. I'll scroll down. Our histogram doesn't look the greatest, but it does look symmetrical, right? There does seem to be a bit of a gap right there, but generally it follows a normal-ish curve. Doesn't look terrible. Our PP plot is hugging the line, but it does deviate a little bit up here, maybe indicating a potential negative skew, but it's not terrible, but it is deviating a little bit from the line, so not the perfect PP plot. Our residual plot actually looks really, really good here. Maybe a couple of values that may be unusually deviant, but then it's hard to tell without more observations. Maybe one up there, but generally where the bulk of it is, right, looks linear, looks like equal variance. Is a bit of a slight bend to it because of probably some sort of independence of observation violation. But generally the scatter plot looks pretty good, right, with a couple of potential unusual observations. So again, if I'm looking to look at this, I might say there's a couple unusual observations. Symmetry actually probably looks the best that we have seen so far. I'm just going to say yes here. Equal variance looks good. All right, any part of X, the differences in Y look pretty good. Looks pretty equal. Linearity looks good as well. Our PP plot is not looking as good, so I'm going to say yes with a question mark. So not just a question mark, but a yes with a question mark. I think it's probably good enough, but it is deviating slightly from our line. Let's take a look at our residual descriptives. Back at our studentized residuals for our second analysis. Let's put it in for our third. Click OK. Not different than 0, negative 0.003 it looks like. Still within 2 times that standard error, so the mean is no different than 0. Standard deviation is closer to 1, 1.008. That looks good. Histogram, again, not looking the best here, a bit of a tail in the negative direction there. We kind of guessed that just based off of what we saw in the last histogram. If I look at that student statistic, I get negative 0.233. Still within 2 times our standard error, so that looks good as well. So a little bit of a tail to the negative direction, but it looks like it's well within what we'd expect by chance. So mean equals 0, yes. Standard deviation, yes. Equals to 1, yes. Normality, yeah, probably close enough. We'll say yes. Again, we can look at our influence diagnostics. We'll sort our studentized residuals for our third analysis. We got a negative 2.64 and we got a negative 2.30. I'll save you again the calculations. You can plug it in, but this is going to be fine. It will be within our cutoff of 3.52. Remember, drop it into your formula to double check it. But I can tell you it does fall within what we would expect to be a value by chance and chance alone. That looks good. Mahalanobis, we can sort ascending. Again, our cutoff was around 14 something. Nowhere near that. Mahalanobis looks good. Cook's distance, again, we're looking for anything that may deviate by a jump. We have 0.06, 0.07, 0.08, 0.09, 0.12, so a little bit of a jump there. Again, if we're being conservative, we would mark participant number 29. So again, I just moved over participant number 29. And then let's look at our leverage. Again, our cutoff we calculated to be 0.27 or 0.28, and we're well within that as well. Okay, so there we go. I know I went a little bit quicker with that one for model number 5, but notice here that we have 5 models. So if you're doing an analysis of your thesis data, your dissertation data, or in your lab, realize you should be spending a lot of time when it comes to checking model assumptions, comparing models to each other. The analysis part should not be a quick process. You figure by the time you clean the data, look at your univariates, look at your different models, check assumptions, you're spending a lot of time in there to try to get a best interpretation of the data that you have. So remember, we came in and we were looking at, can we predict, in this case, sleep hours based on several different variables, whether it was work hours, whether it was social media, whether it was credit hours, right, or study hours. And depending on the model, we got different answers. But really what comes down to is which one is meeting most of our assumptions. It wasn't really until we got to the transform model that we started to get a really good meeting of the model when it comes to assumptions. Still some deviations, but it looked pretty good. We didn't have any predictors that were significant, which again, maybe because they're not significant, right? Maybe they don't predict. Maybe because we had a small sample size, we missed it, right? We did have a R-squared value of 0.10, which is 10% of the variation accounted for by our 4 predictors, but realize it's 4 predictors, so the more predictors you add, even if it's just because of chance, is going to always increase your R-squared value. So even that can be deceptive sometimes when we look at the effect size. Nothing there seemed to be significant. Now we removed that one observation that may be influential. We did get one that approached significance as 0.064, did increase our R-squared value to about 15% of the variation accounted for. But once we isolated that variable, stabilized the coefficient, right? Because again, that coefficient is going to share variation with the other predictors. I remove that noise from the other predictors, and that social media variable dropped off, right? And with a 4% of the variation accounted for, that's a small effect, and so it's not even a moderate effect. And so even with few observations, it doesn't seem like we're picking anything up here. And so if I was to look at all these different models and say, is there anything here, at least based on this sample, that predicts our hours of sleep, I would say probably not, just looking at them and looking at the models that have the best fit when it comes to assumptions, not when it comes to R-squared, but when it comes to assumptions. It's meeting our assumptions better. And it doesn't look like there's really anything predictive here. So if we don't check for these assumptions, right, we may, right, in model number 2, do a little trimming and say, oh, it looks like there's 2 significant predictors. In reality, there may not be, at least not in how we collected the data here and with the number of observations that we have. And so that can lead to, conclusions that end up in published articles that may represent something that may not actually exist in real life. So that's why we're always careful. That's why we always look at our assumptions. That's why we do multiple models, checking assumptions, doing transforms, removing observations, so we can get a holistic look at our data and then come to a reasonable conclusion based on the evidences that are before us. And I guarantee you, if researchers did this on a regular basis, we would have much better research out there. All right, we wouldn't have so many conflicting results, right? We wouldn't have to worry about some relationships being in the literature, but in reality don't actually exist in the population. And so there's a lot of really bad research out there because researchers aren't checking their assumptions. And so we're coming up with conclusions that may not match reality. Okay, so again, I mean, obviously lots of other methodological limitations to this particular analysis that we didn't really even get into, given that it's a student population. Not going to worry about that here. We're just going to look at the numbers and say, like, it looks like of these, model number 5 is probably going to be the one that we would select in this particular case. It doesn't look like there's anything really predictive about these variables, at least in the way that we have measured them. Okay, so we are almost done here. I know I said it'd be around an hour. I think we're a little bit over here, so let's give ourselves another 10 minutes or so. But let's compare at least one of these models. So again, I can look at these and say, like, we don't really have to do a statistical comparison among the models given what we see here with the output. But let's go ahead and do that. Let's go ahead and do one anyway, just for practice. Now remember, when things are all equal, that's when we want to look and see, are there a difference among the models? In this particular case, none of these are really equal to each other. One has significant predictors, this one has 2 significant predictors, this one has 0, this one has 1, right? And so, so in that particular case, there isn't really a comparison that needs to be made here, especially given that these last 3 are meeting our assumptions better than the first 2. So we certainly wouldn't pick the first 2. If I'm choosing between these 3, I think model 5 is showing us there's nothing there. But let's just do a comparison between model 3 and model 4, right? Just for the sake of going through the process so that you know how to do it. So in this particular case, we'll ignore the fact that 1 is a significant predictor and 1 doesn't. Remember, if we're being really strict here with 0.05, then this was a 0. The only reason we put 1 there is because it was close enough for us to investigate further. And upon further investigation, we realized that there's really nothing there. So this is probably as equivalent as we are going to get out of these models here. Okay, so let's go to the PowerPoint just one more time here. Let's look at these last 3 slides. So essentially this is where we're doing that sensitivity analysis. So I already said that you're comparing models. Are the hypothesis conclusions the same or different? Notice here, we notice ours were pretty different going across them. Are the effect size values different from each other? We do see some variation there as well. And then is there a difference in the effect size? Is that statistically significant if you do find a difference in that effect size? This is where we conduct that F-test on the change in the R-squared values. And we do see that. So let's compare models 3 and 4. So we have an R-squared value of 0.1 and we have an R-squared value of 0.15. That gives us a difference of 0.05. Right, 0.15 minus 0.1 gives me 0.05 as a difference in the R-squared value. And so we're going to use this formula here. So we'll go to the next slide. Right, again, all things equal. In this case, not all things were equal, but assuming that they were, we can compare models to each other. And so in this case, we'll take our R-squared value, the change in R-squared, that was 0.05. We're going to multiply it by the degrees of freedom in the residual for the larger degrees of freedom. So in this case, of these 2 models, the 39 is the one that we're going to use as the larger degrees of freedom of the 2 models. And then we're going to divide by 1 minus the R-squared value of the larger R-squared value. So if I look at my 2 R-squared values, the larger one is 0.15, so I'll subtract that from 1. All right, so what that's going to do is it's going to give me so we'll say F here, it's going to give me an F statistic, where we're going to take our change in R-squared, 0.05, times our degrees of freedom of 39, divided by 1 minus the larger R-squared value. So 1 minus 0.15 would give me 0.85. Do our calculations, and I get an F statistic of 2.29. You can check yours, see if you get the same F statistic. Hopefully you do. So 2.29. All right, so once I have that, again, I can then go to this website that is linked here and check to see, is this F statistic, is that a significant F statistic? And if it is, that would tell me that there is a significant difference between my 2 models. In other words, they're not equivalent. All right, so F ratio value in this case is 2.25. Degrees of freedom from the numerator is always going to be 1. That's the degrees of freedom between the comparisons. So I'm comparing 2 models. 2 models minus 1 is going to give me 1. So that's not going to change. And then my denominator in this case is going to be the degrees of freedom for the larger models. In this case, it's going to be 39. Keep our alpha 0.05, and then I'll hit calculate. Oops. Hopefully it shows up here. Yeah, so we get a p-value in this case of 0.14. Again, if I did everything correctly. That p-value obviously is not less than 0.05. So our result is not significant. So no significance here is telling us that models number 3 and 4 are equivalent to each other, that the R squared change, that change in 0.05, is not greater than chance, right? So we increase it from 10% of the variation to 15%, but that increase is not greater than chance. We could expect that to occur, right, within our alpha level. So not greater than chance, these two models appear to be equivalent to each other. So let me go back there. So models 3, models 4 appear to be equivalent, given that F statistic of 2.29. So if that's the case, right, then which one do we prefer? Well, of these two models, we would prefer the one with all of the data. So if they're equivalent to each other, I wouldn't report model number 4, I would report model number 3. Right, because Occam's razor, the simple explanation is best. And so if all things are equal, then model number 3 would be the one that we would report between these two, right? Between models 3 and model 4. They're no different from each other. Now, if there was a difference between them, right, then we could go a little bit further and try to justify which one we're going to use. Again, we always prefer all of our data in our model whenever possible. We also prefer untransformed models and transformed models, again, if all things are equal. In this case, that wasn't the case when it comes to assumptions. But as you can see here, from just this comparison between model 3 and model 4, no significant difference. They appear to be the same when it comes to the R squared value. That increase was not a significant increase. And so of these two, just these two by themselves, we probably say model number 3 would be best between model 3 and model 4. Okay, so again, I just did that last calculation just for practice so that you can see how you can test your models to each other. Again, if I'm looking across all 5 models here, all right, the best model in this case looks like it's model number 5. And in this particular model, it's saying that it doesn't look like there is any statistically significant relationships between our predictor and the outcome. Now, could that change if we got a larger sample size, if we had more variation in sleep hours? Yes, it absolutely could, right? But given what we had with this particular sample, it doesn't look like there's anything there. Okay, so that should wrap us up for this particular lecture. Again, feel free to go back, pause it, rewind, whatever you need to do. If you have questions as you're working on your assignment, let me know. I believe that assignment is due on, let's see, the 21st. Yeah, the 21st. And so let me know if you have any particular questions as you're working on it. Other than that, have a good week. Sorry I wasn't able to be there in class today to explain all this in person, but it did allow us to get it at least on video where you can get kind of caught up and we can get caught up in the class. All right, I wish you well. I look forward to seeing you when I get back. I hope you have a good week. Thank you.